Hello student, today I shall discuss earth magnetism, the second class from magnetism and earth magnetism. Okay, this is my second class from this chapter. So earth magnetism, if we in class 9 or 8 you have seen that if a magnet, bar magnet is suspended from its center of gravity at any point, at any place on the earth, then the magnet will fixed in the north-south direction. Okay, in North Pole, at North Pole of Earth, the North Pole of bar magnet fixed downward, and at South Pole, the South Pole of bar magnet downward. William Gilbert first suggested that if a magnet suspended, then it's always fixed in north-south direction. So he suggested that probably there is a big magnet inside the earth, that is the hidden magnet. Okay, so according to Gilbert, this is an earth, follow, and this is the geographical north GN, and this is geographical south, and here this is geographic magnetic north, and this is magnetic south. Clear? According to, so this is the bar magnet, hidden bar magnet, big magnet inside the earth. Gilbert suggested the north-south pole towards the geographical north and north pole towards the geographical south. Clear? If we suspended a magnet, bar magnet, from its center of gravity at any place, then its north pole, suppose its north pole towards north direction of earth and south pole towards the south direction. Why? Because the hidden magnet, the south pole of the hidden magnet towards the geographical north, so due to magnetic attraction, the south pole will attract the north pole of bar magnet. This south pole will attract the north pole of bar magnet. So the north pole of bar magnet will indicate in the north side, and south pole of the bar magnet will be attracted by the north pole of the hidden magnet. Clear? So according to William, this axis, this is magnetic north. So geographical north and magnetic north are not in the same place. There is an angle. This is the magnetic axis. So the axis through magnetic north and magnetic south is called magnetic axis, and this is called the axis through geographical north and geographic south. This is called geographic axis. Clear? So geographic axis and magnetic axis are not in the same line. There is an angle. If we draw a vertical plane through the magnetic axis, that plane is called magnetic meridian. Magnetic meridian. Similarly, a vertical plane drawn through the geographical north and geographical south, that is geographic axis, is called geographic meridian. Now, so if we follow the figure, this is a plane, this is the this plane through the magnetic axis is called magnetic meridian, and this place is called the geographic meridian. The angle between these two meridians is called the angle of declination. Later I shall discuss it. Okay, so why Earth behaves as a magnet? There are so many opinions, 2 or 3 opinions there are, different type opinion. Inside the Earth, at the center, the molten material, due to high temperature, there are molten material as an fluid at that high temperature, and at this high temperature they are in ionized position, ionized condition. So when Earth rotates in its own axis, the ionized molten material will also rotate. We know the moving charged particle produce current. So due to this current, a magnetic field is produced. So a magnetic field is produced surrounding the Earth. This is one of the opinion. Okay. Second opinion, from the base sun, the high cosmic ray radiation, high energy radiation coming from the base sun, and it strikes the Earth atmosphere, and due to this radiation the Earth atmosphere ionized. So when Earth rotates around its own axis, this ionized air particle rotate with the Earth, and due to this rotation of the charged particle, a current, equivalent current is produced, and due to this a magnetic field is produced. This is another opinion. In another opinion, third opinion, inside the Earth core, the material maximum iron and nickel. So at high temperature, this iron and nickel, when Earth rotates as a dynamo, magnetic field is produced. So at moon, there is no atmosphere at the moon surface, so no magnetic field is there. So magnetic field is produced is a very important point, that due to radiation from the sun, the atmosphere ionized, the air particle ionized, and due to this magnetic field is produced. Okay, now this point, magnetic axis, this term geographic axis, magnetic meridian and geographic meridian. Now we shall discuss the element of Earth magnetism, elements of Earth magnetism. Next point, elements of Earth magnetism. Follow. The physical quantity which describes the total magnetic field of Earth at a place and its direction are called the elements of Earth magnetism. There are 3 types of elements. Number 1, angle of declination. Number 2, angle of inclination or dip, angle of dip. Number 3, horizontal component of Earth magnetism. So these are the 3 physical quantities which are called the elements of Earth magnetism. These 3 physical quantity describes the total Earth magnetic field at a place and its also direction. Now follow, we know the magnetic meridian and geographic meridian, and they are not in the same plane. Suppose this is a magnetic meridian, the plane, vertical plane drawn through the magnetic north pole and magnetic south pole of Earth. That is the line connecting magnetic north pole and magnetic north pole and magnetic south pole of Earth, vertical plane. I have discussed it initially. So this is the north, magnetic north. Clear? This is magnetic north. And another plane follow. This is geographic north, GN. This is geographic north and this is magnetic north. Clear? So this angle is called, this angle, suppose theta. This is angle of declination. So what is the angle of declination? The angle at a place, the angle at any place on the Earth's surface, the angle between magnetic meridian and the geographic meridian is called the angle of declination. Clear? If we suspended a bar magnet from its center of gravity at the magnetic meridian at any place, then suppose this is the direction. This is the direction of total earth magnetism. Clear? This is B. B be the direction of total earth magnetism at this place, at this magnetic meridian. If we suspend a bar magnet from its center of gravity at magnetic meridian at any place, then its north pole, this is the north pole of that magnet and this is the south pole. If this is north polarity in the northern hemisphere, in the southern hemisphere, the south pole will in this direction. In the northern hemisphere, the north pole in this direction. At the northern hemisphere, the north pole will tip into downward, and at the southern hemisphere, south pole of the magnet tips in the downward position. Clear? So this is the magnetic meridian and this is a bar magnet suspended. It is suspended from its center of gravity in this meridian. This is the north pole. So we may come to conclusion that this is the northern hemisphere. Now this angle and this is the, in this direction, the total earth magnetic field B, total earth magnetic field, total earth magnetic field, we consider it is B. So this is the direction of B. This angle, suppose sigma, this is the called angle of inclination or dip. So at any place, the angle between the total earth magnetic field and the horizontal plane in the magnetic meridian of that place is called the angle of dip. In this magnetic meridian, the total magnetic field in this direction B, and this is the horizontal line. This horizontal line and the total magnetic field apart makes an angle sigma. This is the called angle of inclination or angle of dip. Clear? Now, if we resolve the total magnetic field into two components, then this is the vertical component. Suppose V equal to B of sine sigma. Clear? And this is B of cos sigma. This is H. So H equal to B of cos sigma and V equal to B of sine sigma. This is the horizontal component of earth magnetic field. In our daily life, the instrument which is constructed on the basis of magnet, generally this horizontal component of the earth magnetic field is important, because all the instrument, magnetic instrument, the magnet can freely rotate in the horizontal plane, not in vertical plane. They are restricted in the vertical plane. So horizontal plane they are moved. That is why horizontal component is very important. Follow? So what is the horizontal component of earth magnetic field? There are 3 points at any place in the magnetic meridian. If the total earth magnetic field is resolved into 2 components, then the horizontal component is called the horizontal component of earth magnetic field. Clear? These are the 3 earth elements of earth magnetism. Clear? So in a same figure, the 3 elements are indicated. This type of question may arise. Just draw a figure, only one figure, you indicate the 3 elements. Now, this is the earth component, horizontal component, this is angle of dip, and this is angle of dip or angle of inclination, this is angle of declination. Clear? Now, follow. In geographical meridian, this plane is geographical meridian. This is A, suppose OABC. OABC is the magnetic meridian, and ODEC is the geographic meridian. Now follow. In geographic meridian, the vertical component is same. This is also V. But in geographic meridian, the vertical component is follow H cos of theta, that is H cos theta. So B of cos sigma cos theta. So this is another type of question. In geographic meridian and magnetic meridian, the vertical component are same, but horizontal component are different. So this is one type of problem may arise from this theory. How will we calculate the horizontal component in 2 meridian? Clear? Angle of dip, angle of declination, and horizontal component of earth magnetism. Clear? Follow. Now, B square equal to follow H square equal to V square. This is the B square equal to follow H so H square plus V square equal to B square cos square theta plus sin square theta, that is B square. So B equal to root over H square plus V square. In 2 ways we can prove it. Now tan sigma equal to V by H. Tan sigma equal to V by H. If we know the value of V and H, we can find out the value of angle of dip of angle of inclination. Clear? Okay. Now, suppose this is Earth. This is geographical north and this is magnetic north. Follow? The magnetic north and geographic north are not in the same place because there is an angle and it is the angle of declination. Now, this is the hidden magnet. So this plane is called the equator, geographical equator. But what is this is the magnetic axis. So this plane is the magnetic equator. Clear? Magnetic equator. If we draw a plane perpendicular to the magnetic axis, then it is called the magnetic equator. Here, generally magnetic equator is important for this chapter. Magnetic equator, geographic equator. This is magnetic equator, this plane. Now, if we suspended a bar magnet from its center of gravity at the north pole of the northern hemisphere, then the north pole of the bar magnet tips downward. So here the angle of dip, that is angle of declination, equal to 90 degree N at north pole, and at south pole 90 degree S. Clear? So what is the value of angle of dip or angle of inclination at the north pole, at the north pole of the earth, at the north pole of the earth, that is 90 degree N, and at the south pole of the earth 90 degree S, because at north pole the magnet will be in its vertical position and north pole is downward, and at south pole of earth the magnet will also be vertical magnetic axis and south pole is downward. Clear? Because follow, here is south pole and here is north pole according to Gilbert. So if here we magnet placed, the north pole of the magnet is attracted by the south pole, so north pole downward, and here if we place at the southern hemisphere at the south pole, then the south pole of the bar magnet is attracted by the north pole. Clear? This is magnetic equatorial plane. Okay. So at magnetic equator, if we place a magnet or magnetic compass at the equatorial plane of magnetic on the earth surface, the angle of dip will be 0 degree, because the magnet totally here in its horizontal position. Okay, so where the angle of dip is 0 degree? At magnetic equatorial plane, magnetic equator. Okay, at magnetic north pole and at magnetic south pole, the angle of dip 90 degree and 90 degree. Again, an angle of dip or angle of inclination. Now follow, if V equal to H, if vertical component and horizontal component of earth magnet be equal, then V equal to H, then follow V equal to H tan sigma equal to 1, that is sigma equal to 45 degree. So at what place the vertical component and horizontal component of earth magnetism will be equal? At the place where the angle of dip or angle of inclination is 45 degree, maybe 45 degree N or 45 degree S. So suppose the angle of inclination or dip at any place equal to, suppose, 10 degree N. So what do you mean by it? If we suspended a magnet from its center of gravity at this place, and the magnet is allowed to rotate in a vertical plane, then its north pole is downward, tips downward direction and makes an angle, and the axis of the magnet makes an angle 10 degree with the horizontal line in the magnetic meridian at that place. Clear? Again, I repeat again. What do you mean by the angle of inclination at a place is 10 degree N? If we, in first way we make explain in this way, at that place the total earth the angle between the direction of the total earth magnetic field and the horizontal line in the magnetic meridian is 10 degree. And if we suspended a free magnet from its center of gravity at that place, its north pole, it tips downward and makes an angle 10 degree with the horizontal of its axis. Clear? This is the meaning of angle of inclination, that is angle of dip. Another point, suppose a problem, this, suppose the horizontal component of a place, is root 3 times of the vertical component. Suppose a problem, the horizontal component of Earth magnetic field at a place is root 3 times the vertical component. So A is equal to root 3b. What will be the angle of inclination or dip at that place? This is the problem. So A is equal to, we know, B of cos sigma equal to root 3 B of sin sigma, that is tan sigma equal to root 3. So sigma equal to 60 degree. Clear? The horizontal component of a place is root 3 times of the vertical component. So what will be the angle of dip? By angle of inclination, so 60 degree. Clear? Now follow total magnetic field B equal to root over H square plus V square, that is H 3V square plus V square equal to 2V. Follow? B equal to 2V. This is another relation. Okay. So suppose V equal to, at that place, 0.3 Tesla, 0.3 Oersted, Oersted in SIC, CJ system, Oersted. So what will be the value of B? From here we can find out the value of B. And here the horizontal component, if the angle of declination, suppose angle of declination equal to 10 degree. 10 degree is, so what will be the value of horizontal component of Earth magnetic field in the geographic meridian? So geographic meridian, horizontal component of Earth magnetic field, H cos of sigma into cos of 10 degree. Clear? Putting the value of H, putting the value of sigma, putting the, we will get the horizontal component of Earth magnetic field in the geographic meridian. Follow? H cos theta. So in this H cos theta, value of a V cos sigma into, so H, sorry, B cos sigma into cos 10 degree. Clear? This type of problem may arise. Now, a problem, very important problem. Suppose that two vertical plane makes an angle 90 degree to each other. This is a actual magnetic meridian. Suppose problem, follow the problem at first. This is magnetic north, this is magnetic meridian. This is a plane. This is a plane vertical. Okay? And another plane, I draw with dotted line. These two planes makes an angle 90 degree. Apparent plane. This is the magnetic meridian. This is magnetic north. This plane is magnetic meridian, and thus two arbitrary plane, this vertical plane makes an angle 90 degree. If the angle of dip sigma, and in this plane the apparent angle of dip sigma 1, and in this plane apparent angle of dip sigma 2, then what will be the relation between sigma 1 and sigma 2? The relation will be cos square sigma 1 plus cos square sigma 2 equal to cos square sigma. This is a maybe this type of question may set in MCQ and broad question also. Again, I repeat again the question problem. Follow: the two vertical plane makes an angle 90 degree with each other, and the apparent angle of dip at the two plane is sigma 1 and sigma 2. If the actual angle of dip sigma at that place, then what is the relation between sigma 1 and sigma 2? Clear? Suppose first plane makes an angle theta with the original magnetic meridian. The first plane makes an angle theta with the magnetic meridian. So second plane will make the angle 90 degree minus theta. Clear? Follow? In three plane, the vertical component is same. So for the first and horizontal component, suppose H, here H, here H1, and horizontal component here H2. Suppose in magnetic meridian, the vertical component of earth magnetism V is same in three plane, but horizontal component in the magnetic meridian H, in the first plane horizontal component H1, in the second plane all are apparent of course H2. So we know that tan sigma equal to V by H, cot sigma equal to H by V. Clear? And in first plane